I'm so excited to have everyone back for day 2. I hope that your morning sessions today were really great and that you got a lot out of yesterday's sessions as well. So yesterday we set the stage by thinking about innovation and frontiers generally with great talks by Twyla and Caitlin. And today we're going to dive deeper and look at frontiers in artificial intelligence and machine learning. Feel free in the chat right now to share some of your favorite moments from yesterday with us so we know what things really resonated with you. And we aim to continue our networking today at today's coffee break after this plenary, where you can form small groups and chat about various topics with each other. And we also hope that you will join us tonight for our research showcase, which is also a great opportunity to hear about latest innovations and frontier research that's happening. And it's also a great opportunity to meet new people and have small group conversations, which we're really trying to focus on this week. So something that I didn't get to yesterday was to highlight Esip's community participation guidelines. I'm going to share my screen real quickly so that you can get a look at those. So these are part of your registration form when you join, but I know that we're busy and maybe they were overlooked by just a couple of folks. It's really important that we emphasize this. And so I'm going to read from the purpose of the guidelines. The purpose states that the heart of Esip is people, and I think we all know that. We put people first and do our best to recognize, appreciate, and respect the diversity of our global contributors. Esip welcomes contributions from everyone who shares our goals and wants to contribute in a healthy and constructive manner. As such, we have adopted these community participation guidelines as our code of conduct and require all those who participate to agree and adhere to these guidelines in order to help us create a safe and positive community experience for all. The Esip community participation guidelines describe expected behaviors, as you see here, and responsibilities when involved with Esip activities. The Esip community participation guidelines for me, they go beyond a code of conduct, but they include reporting and consequences for unacceptable behavior. Should you witness or experience behaviors that are not acceptable, I want you to contact me or a member of the Esip staff or our board, or you can visit this link to learn more about third-party reporting. While it can be uncomfortable to discuss, I want to do everything in my power to make sure that Esip is a welcoming, open, and safe community. This takes effort and work, and I appreciate all of you and your help in making this possible. Now, it is my pleasure to introduce Esip's president, Tamara Ledley, to kick off our plenary session today.
Thank you, Susan. I welcome everybody to the second day of the Esip meeting. It's been my pleasure to serve as Esip's president. In doing so, I've played a large role in shaping Esip's new strategic themes, and in the selection of the theme for this year, leading innovation in earth science data frontiers. One of the most game-changing of those frontiers is the fast-paced world of artificial intelligence and machine learning, AI and ML. As humans, there are limits to how much one person can do in a day or process in a set period of time. By exploring the frontiers of computing, we can take what would be a tsunami of data and efficiently turn it into actionable knowledge. I'm pleased to introduce you to our speakers today. First, we have Hannah Kerner, assistant professor with NASA Harvest and the University of Maryland, to talk to us about the power of machine learning and Earth observations to enhance global food security. Following Hannah, we will have Lyndon Estes, assistant professor at Clark University, to share about harnessing small satellites and machine learning to create high-resolution annual maps of small-scale croplands. And finally, we will have Lexi Yang, a research scientist with Oak Ridge National Laboratory GeoAI Group, to share how GeoAI is revolutionizing how we connect the world. We will take questions after each talk, so please use the Slido tab to record your questions and vote up others' questions. At the close, we hope to have some time for small group discussions or follow-up questions with the panelists as a group. So now I will turn it over to Hannah.
Hi, everybody. Just want to confirm that you can hear me and that we can see my slides.
You
We
look
can hear
great
you.
and sound great.
Oh,
Awesome.
yep.
Thank you. Okay, so in this talk today, I'm going to be telling you a bit about what we're doing at NASA Harvest to harness the power of machine learning and Earth observations for enhancing global food security. First, I'll tell you a bit about what NASA Harvest is. So NASA Harvest is NASA Applied Sciences program on agriculture and food security. And the goal of this program is to enable and advance the adoption of satellite Earth observations to benefit food security, agriculture, and human and environmental resiliency. And unlike other NASA programs, Harvest is run as a consortium out of UMD. So we have a hub of researchers at UMD that do research, but we also have many partners outside of UMD at private companies, government agencies, other universities, all kinds of entities that are also working to achieve these goals together. And I just want to highlight here at the bottom some of the people that are part of the Harvest Hub at UMD who have contributed to the work that I'm going to be sharing today. So NASA Harvest really has a global reach, and we have some projects like the Crop Monitor program that really reach almost every country in the world. But here with these icons, I've shown the countries where we currently have kind of major analytics projects going. And what you'll notice is that there are a lot of icons here. And so we are doing a lot of really impactful projects with different countries to help them to monitor, help the governments, help growers, help other agencies to monitor the status of food security and crops in the region. And the demand for this kind of analytics is really only growing right now as traditional survey-based methods become challenged by pandemics and travel restrictions, conflict that might make data collection dangerous in some parts of the world, and cost and other factors. So when we're doing these global projects, we have kind of many choices of Earth observation data sets. All of you, I'm sure, are very familiar with all of these different options. But here I'm just kind of going to discuss the trade-offs between these for the work that we're doing. So we have a range of spatial resolutions from MODIS on one side at the coarse resolution, all the way down to sub-meter imagery that we get from providers like Maxar or SkySat from Planet. And in between, we have kind of a spread between high resolution and medium resolution satellites. These satellites also have different temporal resolutions. So some might have daily resolution, some have less frequent revisit times, some are targeted on an as needed basis. And this really plays a lot into our decision of what source to use, because in agriculture, we're really trying to capture these fast changing dynamics while crops are growing during the season. Another trade-off is, of course, cost. So some of these, like the MODIS, Landsat, and Sentinel satellites are all free and publicly available, whereas the higher resolution satellites can be quite costly, especially when we're starting to scale these projects over large countries and many countries. And finally, we have trade-offs in the spectral resolution or the spectral availability. And so what I want to show with this is that they're kind of in the middle of these here with the Landsat and Sentinel satellites. Given the global nature of what we're doing, the Landsat and Sentinel satellites are really in the sweet spot for most of the projects that we're working on at Harvest. We definitely make use of these other sources, MODIS, PlanetScope, and Maxar's sub-meter data for certain projects and as needed, but for these large scale monitoring projects to deliver insights at a resolution that's relevant for stakeholders and decision makers while also spanning very large regions. These are typically the satellites that we're working with. So I'm going to go through some of these highlights from the last year of what we've been doing at Harvest. 3 of these projects, one is in the US Corn Belt, one is in Togo in West Africa, and one is in Kenya in East Africa. So in the United States, one of our major priorities is to do in-season crop type mapping and crop conditions assessments in order to provide information to help stabilize commodities markets who are looking for information about how these key crops, corn and soybeans, are doing. And this is important in the United States because the US is a major exporter, one of the largest exporters of corn and soybeans. And so market activities globally and their prices are really driven by the public information that's available about these key crops. For example, the USDA and FSA put out reports that have a big influence on market decisions. And during the growing season, this information is pretty intermittent and can be highly uncertain, especially when shocks occur that cause additional uncertainty. So for example, in 2019, there was record flooding in the early spring that caused late planting and a record number of prevent plant acres. And then in 2020, we had both the COVID-19 pandemic, which really challenged traditional USDA survey methods, as well as a derecho and a drought even in Iowa in August of 2020 as well. And so these events really add additional uncertainty to an already uncertain system. And so, for example, recently we've seen that corn and soy prices are really fluctuating right now. We're seeing record lows earlier in the growing season and then record highs now because the estimates of how much production there will be of these crops is changing. And so the markets are responding to that. And so what we want to do is use Earth observations to provide in-season estimates of these factors that are important to the markets and to other agencies so that we can help to stabilize this decision-making and stabilize these prices. So back in August, when this derecho, a high-speed windstorm, hit Iowa and exacted a large amount of damage on crops there, we immediately looked to Earth observations to assess the impact of that storm. So this image is showing a Sentinel-1 image before the derecho, and then after the derecho, we see huge changes in the signal from Sentinel-1, which is synthetic aperture radar, really measuring the textural response or the textural changes from those crops. And so we use Sentinel-1 in order to map the extent of the derecho damage. And then we used the harmonized Landsat and Sentinel-2 data set to, alongside with our deep learning method that we've developed for in-season crop type mapping, to create a map in the middle of the season of where corn and soybeans were growing, and then use that to generate estimates of how much of the storm impacted corn and soybeans. And so then we're able to deliver this information publicly and, in the future, hopefully help to provide these estimates operationally so that we can help stabilize prices as well as help government agencies to assess the damage. In Togo, we worked on a project earlier in the spring of last year at sort of the beginning of the first peak of the pandemic, where the Togolese government contacted us because they were launching a program that would be distributing loans to smallholder farmers to help them purchase supplies to boost production during the pandemic. This program is called YOLIM. But the problem they had was that in the census records or the government voting records that they had, they really weren't capturing what they thought was the true population of smallholder and subsistence farmers. And that's because they only had records of farmers that reported farming as their primary income. And a lot of smallholder farmers are doing subsistence farming, or only serving, a few neighbors or their families. And so these secondary occupation farmers were not captured in the surveys. So what we did with this project was to use machine learning to develop a map of all of the cropland in Togo in under 10 days. So again, this rapid response type of effort and way of leveraging Earth observations data is really only possible with machine learning. There's no way we could analyze this scale of data without it. And so what we did was we used SkySat data at around 1 meter per pixel resolution to rapidly do some labeling of training data as well as reference data for assessing the accuracy of our map. And we use Sentinel-2 data for actually doing the mapping or as the input to our classifiers. And so we generated this map that you can see here and is also publicly available on Google Earth Engine and other websites online. And in Kenya, we started working on a project called Eofarm, Earth Observations for Agricultural Resource Monitoring. This is a project supported by the Swiss Re Foundation and other partners, really to address this need that is really urgent in many countries that are at risk of food security or food insecurity, to be able to monitor crops both during the season, at the end of the season, in order to assess what the national food budgets are, how much of these crops is available, what production is going to be, and even to have early warning systems for where people may need some additional assistance. So through this project, so far we've been creating cropland maps for the end of season across the entire country. At the 10 meter resolution, which is really unprecedented for many countries. And so we again have this publicly available map for Kenya. We also were doing in-season cropland mapping for the 2020 season. And we're also creating crop type maps of key food security crops such as maize, also at the 10 meter resolution with Sentinel-2 images. And in addition to creating these maps, we're putting a lot of effort into, how do we take these systems, rather than just publishing the maps, how do we make systems that will really be able to be run by the stakeholders and by people in country, so that they're not just relying on us to generate the models, and they can actually learn to do this themselves and be able to run these models and create their own maps in the future. So all of these projects that I've discussed and the projects that we're working on for enhancing food security using machine learning and Earth observations data, we run into a lot of challenges that I think are pretty common actually across remote sensing applications. The big one that many people in this audience I'm sure have faced is the lack of labeled or ground truth data, especially in regions outside of the US or Europe, where we have labels for training our models and validating our models. So this, again, was the case when we needed to create this cropland map of Togo. There's no data set of labeled locations where crops and not crops are in Togo. And so our approach here was to do something called multitask learning, where the goal is to jointly train a model to learn multiple tasks and learn features that are shared across all of those tasks and can be used to inform one another. So in this approach, we have a multi-headed LSTM, where one head of the network is classifying global, diverse, crowdsourced examples from the GeoWiki crop dataset. And then the other head of the model is classifying the local cropland examples. And these, the difference in the size here, to give you an idea, is usually about 35,000 examples for the global head, which learns, what does cropland look like in general everywhere? And then in the local head, we have maybe a few hundred or less examples that the model learns from. And so this is the approach that we use to create this map for Togo. And we've also now demonstrated using this map in many other countries, including China, Ethiopia, Sudan, and of course, Kenya. Another approach we're working on is called meta-learning. And the reason we're using meta-learning is actually for crop type mapping, where in the case I just discussed with the multi-headed LSTM, I said maybe we have a few hundred samples, but for crop type mapping, we're usually in a case where we maybe have dozens or less than 100 examples, very few to learn from, and we want to be able to generalize very quickly. And so the approach we use for that, called meta-learning, is really learning to learn. So the idea is that we take all of these data sets that we have globally available in different contexts, but related problems, and we learn model parameters that are optimizing learning quickly in each of these new tasks. So we're learning kind of starting parameters that will enable the model to learn in as few examples, or learn in very few examples for a new task. And so then once we have this trained meta-learning model, we can take a very small data set, for example, less than 100 maize samples in Kenya, and very quickly generalize to learn from that small amount of samples to create a map of maize in the whole region. And so this is the approach that we use for mapping crop types, and not just maize, but other crop types as well. On the data side of things, so these two approaches are really using innovative machine learning methods to address the low data problem. But on the data side, we're also trying to develop creative ways to collect ground data in ways that really increase the amount of samples that we're capable of getting, not just in certain regions, but globally. And so one approach for that we're developing is looking at Street View images from Google Street View, as well as car-mounted GoPro images, which is part of a Lacuna Fund award that was recently awarded to Catherine Nakalembe in our group. And the idea here is that we actually right now have cars driving around in Kenya as a pilot region with GoPros mounted on top of the cars. And then we're developing machine learning models that will segment out where in those images the crops are and estimate the distance to those crops so that we can move our point from where the camera location is into the field. And so the idea is to really increase the amount of data that we can collect in a transformational way. Another challenge for machine learning is that the real world is not ImageNet, right? And so much of machine learning methods have been developed really for using and being tested with these benchmark data sets like ImageNet or CFAR10. And so these are very different than the kinds of data sets that we have in remote sensing. There's high interclass variance and low interclass variance in a lot of what we're looking at. We often have unclear labels to assign to an image. So here in these examples, I'm showing some intercropped fields in Uganda and Kenya. So, just this field alone probably has at least 3 crops growing in it on the bottom. Our labels are dynamic. So a label might be maize one year, but the next year it's changed to some other crop type, or maybe it's not cropland anymore at all. So we have this dynamic aspect to our labels, in addition to a lot of noise that's involved in crowdsourcing or field data collection. And finally, there are also ground truth labels can be difficult and expensive to acquire and sometimes even dangerous. And so, I also sometimes question the ethics of trying to collect very large data sets when it's not very accessible to do so. So I really think that benchmark data sets are useful, but I think we should be careful to not try to force the real world into machine learning's constraints, but rather force machine learning into the real world's constraints. We also have big challenges in spatial and temporal generalization. Agriculture looks extremely different in many different places in the world, not just in the spatial patterns, but in the sizes. Here I'm showing this little size of a football field is a tiny fragment of an Illinois field, but in Ethiopia, this same square covers a much larger number of fields. And, we also have domain shifts in between seasons where, for example, early or late planting will cause fields to look very different at the same time in the growing season. Our evaluation metrics are often not capturing the real world performance that we see spatially with these maps. So usually machine learning, we're using these sparse test data sets that maybe have a few hundred, or if we're very lucky, a few thousand examples, and you might have a great accuracy on that. But those point-based data sets are not really testing the artifacts and spatially correlated errors that we see in the maps. And so this makes iterating on model development even more challenging. I think we can do a lot better in our community of having a culture of open data and open code and sharing. We need to be able to reuse other people's code and be able to build off of this state of the art and intercompare published methods and be able to access the maps that are produced. I think the community is really moving in that direction now, and efforts like the Lacuna Fund and Radiant Earth ML Hub are helping with that. So I think that's great, and we need more of those kinds of things. And then finally, deploying machine learning models in the real world is just really hard. I think people dramatically underestimate the amount of effort that it requires to go from a model that you've tested with your test data set and gets good performance to actually having a model that people are using in the real world to make decisions based on. I found this quote from deeplearning.ai based on a study saying that only 22% of companies that are using machine learning have actually deployed a successful model. And I think that really illustrates the difficulty of doing so. So finally, I just want to end with this quote from China Lawson, the Togolese Minister of Post-Digital Economy and Technological Innovation, where she said, based on this map that we were able to generate, this map provides unmatched clarity into the nature and distribution of agricultural land nationwide and helps provide decisive knowledge being used to design the social protection policies aimed at improving the lives of agrarian rural communities. And so to think about in the rest of this meeting or in our discussion, what is it going to take to realize the impact that remote sensing and machine learning can have, like in this project in Togo, but in so many other places on global food security, but generally for social good. And so just to capture what I discussed, I think mitigating the training data bottleneck, having open data, open methods, creating flexible tools and processing chains for scaling our analyses globally, having interdisciplinary teams that combine machine learning researchers with the domain scientists, and doing capacity building and engaging stakeholders from the very beginning. All of these are what we need to do to really realize that benefit. So with that, I'm going to end, and thank you all so much for your time. And I'm going to turn it over to Lyndon.
Hold on, Hannah.
Oh,
don't
sorry,
turn it over to Lyndon yet.
I'm still. Yep.
No worries. We just want to make sure we have time to ask a couple of questions of you. Before I jump in, I want to remind everyone to go over to Slido. There's a bunch of questions in there, and I invite you to add some more or upvote them. But maybe we'll start with this first one that's received 5 upvotes while others are looking over there. So first, thanks, Hannah, for a great talk. And I think that quote from the Togo minister was really profound in terms of the impact that the NASA Harvest Project has in your work. So thank you for sharing that. So one question says, can you expand on the ethics of collecting large data sets? Is it the inability to accurately ground truth?
Yeah, so there is a lot of difficulty in collecting ground truth data sets, especially in areas that don't have great connectivity. So, you know, we have a lot of noise in these data sets, for example, because if the GPS error is off, well, a 3-meter GPS error could mean you're in somebody else's field, or it could mean that you're on the road or somewhere else entirely. And so there's a lot of challenges in general for collecting ground truth data sets in a lot of parts of the world. But also, you know, a lot of the areas where we're working in, we're trying to use Earth observation data because it's difficult to get to those regions in the first place, or it's dangerous for survey methods to be conducted throughout households, for example, where we're working in Mali with USAID as a NASA Harvest project to monitor crops there. We're doing this because it's too dangerous for them to do these traditional survey-based methods. Mm-hmm. And so if we're wanting to use these machine learning algorithms that, like a deep learning classifier that requires thousands and thousands of labels, you know, I think it's really important practically, but also ethically, to find ways to use less data or require less data from the local region. You know, I think we shouldn't be, you know, trying to make the real world work for machine learning by saying, okay, well, we need to find a way to collect 10,000 field data points in Mali. You know, I think we can really find a way to make the machine learning work for us and be innovative with what data we do have available.
Mm-hmm. And it sounds like with the multitask learning and the meta learning models, that's what you were speaking to.
Yeah. And again, in a rapid response context, you can't even go get that data if you wanted to. So that's really what drives those solutions.
Gotcha. So another question from Slido that's been upvoted is, how do harvest analysis products interface with USDA's own analysis, for example, the FAS crop monitoring efforts?
Mm-hmm. Yeah, so we have a great relationship with USDA, and we work with them a lot, their remote sensing team as well. And, you know, really what we're trying to provide is like an additional set of data points. Right, there's, you know, the public has access to information from USDA, FSA, other sources. And when you can see that us and all these other sources are in agreement, then I think that can be a sign of, okay, there's not too much craziness going on. There's not going to be a lot of fluctuation. Maybe everyone's in agreement, hopefully. And so probably those estimates are all fairly accurate. But if there's a lot of disagreement between all these different data points, then maybe something else is going on there. So, you know, our goal is really to collaborate with them and help provide additional data, not so much be redundant or integrate the two, really.
Gotcha. All right, well, we have time for one more question. I'm going to make it hopefully an easy one. And then what I hope to do is if you could check the other questions out in Slido and then maybe paste the question, and if you have time, the answer in chat so people can see those. But we know that's a big lift, so whatever you can answer. So the last question is just, where do you archive your training data, and is it publicly available?
It is, yes. So some data that we collect in the field from partners, we don't have the ability to make publicly available because we don't own the data. But whenever we can, and any data that we can make public, we do. And all of that is linked in our papers. There's a Zenodo link to them in our papers. And I can paste the link to the papers on the chat.
I found one that was at Archive that I think was your most recent one. So if you want to check that, hopefully I got the right one.
Yeah, the rapid response one is the Togo one. And then we have one from NURIPS about Kenya. And
any of those links would be fantastic. I'm sure the data links, we always like to hear that your data are linked from that using Zenodo. So that's great. All right, well, please, let's give a round of applause using your reaction button or hands if your video is on. That was a really fantastic talk, Hannah. Thank you so much. There, look at all those thumbs up and claps that are happening. So with that, thank you again. And you could check out those questions in Slido, and I will turn it over to Lyndon. Let's see, we can see you, Lyndon. Do you want to do a quick, let me see if I could hear you.
Yeah, hi, can you hear me?
You bet.
All right, thanks. I'm just going to share my screen here quickly.
Uh-huh.
And can you see that?
Yep, you are, let's see. Oh, yep, now it is full screen and we could see you. So take it away.
Okay, thank you. So, and thanks for the invite to be here. And so I just want to start by acknowledging the sort of hard work and innovation by a number of colleagues and collaborators at multiple institutions, including my own Clark University, but people in Kenya helping us a lot with this work as well. So it's a big effort that's gone into what I'm presenting today. Also support from a number of key partners, particularly Omidyar Network's Property Rights Initiative, which is now Place Fund. NASA and Esip have contributed this, Amazon Web Services, Planet by the Education and Research License, and a number of others listed there. So I'm going to start from sort of the perspective of trying to understand global change. So the past decade really has been sort of seen I would say, argue a revolution in the ability to understand sort of annual to sub-decadal changes in the land surface globally, such as this deforestation. And that's really been enabled by the availability of the moderate resolution Landsat and now Sentinel archives, the pre-processing of those to higher levels of higher pre-processing standards, and then the combining of those with web-based processing platform. That really enables things like the global forest change product, surface water change, et cetera. So in my talk today, I'm going to pick up on a theme that Hannah talked about. I'm going to talk about sort of recent innovations in the past 5 years that allow us to get at a particular aspect of global change, which is sort of change in highly dynamic land cover types, using sort of the newest sensing technologies, imaging technologies, and some of the newest machine learning approaches. So the global change I'm particularly interested in is rapid agricultural change, particularly in Africa, where we expect probably on the order of at least 140 million hectares of new cropland to be developed in the next couple decades. That's an area about the size of 1/5 or 1/4 of the lower 48 of the United States. And that's due to a probably expected tripling in food demand by 2050, plus the fact that the continent's got 1/3 of the world's remaining potential cropland. So that's going to be a pretty big change. And so it's not just going to be expansion, but the sort of characteristics of those croplands are going to change as well. And if you really want to understand agricultural change, which is the theme of my work, it depends on having several critical data sets that you can only really develop with remote sensing. And there's sort of two key ones at the foundation, which are understanding both the location of croplands accurately, getting a good handle on that, what the characteristics of the fields are like in that. As you've seen from Hannah's talk, they'd be quite variable. And then you build on top of that crop type maps and crop yields. And so you want to get this on an annual basis to understand the nature of those changes. So that's quite complicated, difficult to do in a place like Africa, where most of the croplands at the moment are small scale in nature, and they're really dynamic in both time and space. And so you've got a definitional problem to start off with. So if you look at this image here, it's in over Ghana, the top row of images. You look at these fields here, and it's actually making a decision, whether on the ground or up in space, as to what's active crop field, what's fallow, what's been abandoned, and making that definition affects how you map things to start. And those definitions are always changing. On top of that, you have pretty rapid change happening between years. Like you can have in a 5-year period of time now a rapid shift from, say, a small scale agricultural system on the left here in the lower left towards something that looks completely different. The location and shape of the croplands change in just a 5 or 6 year period. Now we have a center pivot agriculture that's replacing these small scale croplands. So that's sort of the change signal that one wants to know, but complicating that is the fact that these systems are dynamic within the course of a year themselves. So if you want to capture characteristics of cropland within a single agricultural year, you look at it in the growing season, sort of lower right, the left-hand image, and I hope people can see my cursor. yeah, that's the growing season in 2018, and this is the dry season immediately after that. And you can see, if you want to get a handle on what an individual field looks like, they look different between both seasons. You know, they're different shapes. So that's quite a challenge. So these croplands are really dynamic, and that makes remote sensing of them, accurate remote sensing of them, you know, very difficult. I would put that down to three major reasons. The first is that the imagery that we typically have available, I would argue, to study these things at large extents, is often inadequately scaled for the task. The resolution, spatially in some cases, might be too low to get at those smallest field size classes. And if it's not, you often have inadequate frequency, particularly in cloudy regions, where if you want to look at the agriculture within a single year and develop a good cloud-free look at it, at least optically, you don't have enough image density to get that image. Secondly, the characteristics of the fields themselves are pretty confusing for our mapping algorithms. They're small, indistinct boundaries. They blend in a lot with particularly savanna vegetation. So it's a sort of algorithmic challenge, which is compounded by what's already been mentioned, which is the fact that training data are really hard and expensive to get. So these three problems are a big challenge. The good news is that just, you know, sort of in the past 3 to 5 years, at least the imaging and the computational problems are a lot better addressed now. So talking particularly about new small sat fleets of the type put up by Planet, that are small, low cost, they're high, not very high resolution, but high resolution spatially, and, you know, high temporal resolution, which is really critical, that allow you to address that scaling challenge. And then the algorithms are just they're really developing rapidly now and helping to make sense of patterns in that imagery. So what we've done is we've tried to bring together some of these advances in a field mapping platform that we've been developing over the past few years, which has 4 main components. And the intent of this is supposed to be a system that both gets the location and characteristics of croplands, gets that done more accurately. So our image processing software is designed to work with PlanetScope daily data, convert that into seasonal composites that represent a single agricultural year. And we pass that into a labeling platform that we've developed for collecting training data, designed to collect training data for a machine learning algorithm that minimizes some of the error inherent in collecting those labels. This interacts with the machine learning process itself in something we call active learning, where we have the machine learning makes a prediction and identifies the areas where it's doing most poorly and sends these back in an automated way to our mapping teams to collect new labels in those areas. And that iterates until the model is more accurate. And then finally, we pass that into a segmentation algorithm to identify individual boundaries of fields or individual fields, or get as close to that as we can to get at the characteristics of the croplands. So we've done this and tested it by applying it to Ghana, right next door to Togo there. Which is a good place to test how effective this type of mapping approach is. Ghana represents a range of agricultural conditions, sort of from this very cloudy forest zone down in the southwest, all the way up to savanna agriculture in the northeast. We broke this up into 16 mapping blocks and ran our machine learning processes in these. So just to quickly show you a couple components of that. So here's our image processing, which basically what we do is we take a tile of about 5 by 5 kilometers squared, and we intercept every single PlanetScope image that in a 5-month period for the growing season and a 3 to 4 month period in the dry season that follows it immediately. And we convert that to analysis ready data, and then we run a temporal compositing algorithm that we developed to create the cloud-free growing season and off-growing season composites. I just want to stop here and sort of highlight the fact that that daily resolution of PlanetScope is really critical for this process. These 2 images here show you the density of images available for download in the PlanetScope catalog for these 2 time windows I showed you, May to September 2018 and December 2018 to February 2019, which are the 2 periods of interest for us. And you can see that there's a lot of variability because of cloud contamination, that sort of thing, of what planet was made available because they consider it to be usable. And so there's some places where you actually have far less than daily density. And so if you go to less than frequent than daily imaging, to say 5 daily imaging, you start to break down your ability to get a good cloud-free composite over, for this type of time window. So that daily thing is really critical. So just going on to our next component, the labeling platform. So after we create our composites, we present them to our labeling team in a web-based interface that we developed, which has digitizing tools. Our teams look at the PlanetScope imagery and digitize fields in them. We assess the accuracy of each of our labelers, and then we have multiple people look at the same site and label it, and then we convert that into a consensus label that sort of merges them into a best guess as to what a field should be. And that helps minimize a lot of that labeling error to get more accurate training data. Our active learning process, which is at the moment is just featuring a simple sort of random forest model that is, interacting with the labeling teams. It sort of iteratively sharpens itself. So in the first iteration after a random generation of training data, you can see this prediction of pixel-wise prediction of cropland probability. It looks, if you look at the map, it's got a lot of salt and pepper and noise in it. By the time you get to the 4th iteration, the accuracy's improved, it's a lot sharper. And so you have a better overall classification, which you can see quantitatively. This is the sort of progress of our accuracy and F1 scores for each of our mapping blocks, with the black line showing the average across that. And you can see that there's a general increase in accuracy for both and F1 score, which doesn't look like a really great slope of increase, but we've tested it versus randomly selected sites, and it is a larger overall accuracy increase and a faster overall accuracy increase. And you get a sense of the areas that the model struggles in. These are showing you the selection of sites by the model for each iteration, and you can start to identify places in the mapping blocks that cause the model problems. And so then we finally end up with this segmentation. And this is the final map. This is generated from our posterior segmentation of the cropland predictions. And this is converted to field density here, but you get a sense of the detail you get in these inset maps. And so how well do we do in characterizing the characteristics of the croplands in terms of the average field size? That's a look at that here. We can compare the average size of our segmentation polygons from the machine learning process against the best labels generated by our workers over validation sites to get a sense of how well the size class distributions map up in each of these mapping blocks. And in some places, we are actually substantially overestimating what should be an average field size. So we have work to do. As you've seen, our accuracies are only around 80% for the machine learning process, and we're overestimating. So that brings us to what can we do with newer generations of classifiers, particularly deep learning ones. So we've been replacing our random forest model in our active learning process with convolutional neural nets, particularly UNets, starting off with those now, and testing to see how well those improve things. And a simple comparison, a simple and early comparison of what we get with random forest versus a UNet shows that it's quite a dramatic improvement. We have sort of a 12 percentage point increase in the accuracy. And you can see from the UNet predictions, they're much sharper and crisper than what you get with the random forest, and far less commission error. So that's really helping us a lot to improve things. And so we're busy in the process. We're still testing a lot of these new architectures. But what we're also doing is simply trying to vary how we train the model. So we've got 2 ways of training it. One is with binary labels. So cropland, not cropland. We're training the UNet with that, versus a 3-class approach where we train the model to recognize the edge of a field, the interior of it, and then what's not a cropland around it. And you can see the difference in the predictions between these 2 approaches. The binary labels on the left sort of the third column, and the 3-class trained model, that's the interior field class resulting from that model. And you can see it starts to break up the fields into what are clearly recognizable objects within these images, which helps us get a much better segmentation. And so we merge those predictions with our segmentation approach, and we get things that start to look a lot more like individual field objects that help us get to something which is probably much closer to what an actual farmer's field is, although it won't ever get there entirely. So that's what we're doing now. There's a closer up look at that to show you some of the detail you're getting. And so we're busy moving forward with that. So we're in the process of identifying the final sort of model architecture we want to do to make our generation 2 field boundary maps of Ghana. And then we want to expand to other countries. We've already done a little bit of testing in Republic of Congo and Tanzania. We'd like to expand that more fully. We're also starting to use those as filters for training crop type mapping models, which I'm not talking about today, but that's a project that's ongoing now that's supporting a Gates Foundation project that is led by Farmerline in Ghana. And once we have that, we can create annually updated maps, since we can map cropland in a single year, and then we can really start to use that to evaluate cropland change and its consequences. And so that's where we're moving. But what I want to do just is to sort of end with 2 final points of what I see as being major remaining bottlenecks and opportunities. So coming back to this diagram for why it's difficult to remotely sense small-scale croplands, I would argue the first 2 problems are starting to get pretty good solutions to them with these new sources of data that are being launched in ever-increasing numbers, more and more platforms for collecting high spatial temporal resolution data. And then the algorithms are really making big strides. And we're just working with some of the more common recent new ones and getting good results from those. The bottleneck that remains is something that Hannah already talked about. It's training data. That's an old school problem. And despite our best efforts, it's really sort of the thing we spend the most time on. And the approach we're using now with this sort of 3-class UNet model, it actually makes the training data problem harder because we have to map much more precisely when we're collecting our training data. So the labeling task itself is really quite difficult. So this is our labeling platform, which really requires people to look at multiple renderings, multiple seasons of the PlanetScope image, toggle back and look at the base map imagery that you have there to get a sense of what fields might look like in PlanetScope, which is lower resolution, and then to try and make your best guess, an educated and informed guess as to what is the boundary of an individual field within that. And that's quite difficult. It leads to error. And the result is that we often have generally lower quality labels, not because our mappers are bad, they do great work. It's just because it's a hard task. And there's a lot of interpretation that goes into it. And so this is, like I said, we track the accuracy against reference labels in our system, in our labeling platform. And this is the distribution of scores that our mapping team gets over time. And you can see there's a lot of variability in a score that ranges from 0 to 1. And the average tends to be somewhere between like 0.75 to 0.65. And so that means our labels have quality issues. You get a sense of that, the agreement here. We have multiple people look at each site when they're doing labeling. And this is a map of label risk. So the redder it is, the more the people that map that site tended to disagree as to what was a field or not a field in that area. So you can see there's a lot of red and sort of this intermediate white color, which means we have a lot of disagreement on the labels. And that translates into real world impacts on your, this is pretty obvious. I think you get garbage in and garbage out is the old saying, but here we can quantify it, how much that affects our mapping accuracy. So if we train a model, this is the random forest here with the least accurate mappers labels, we get a map that looks very uncertain and can't really recognize the fields well. You compare that to more accurate labels, or maps, models trained with our consensus labels, it looks a lot sharper, and it's about 15 percentage points more accurate. And so that's a big difference. Problem is now is we're finding that promising UNet approach is probably even more sensitive to the label quality. So we have to remap everything much more carefully now to get good training data. So second thing I wanted to highlight and end on is the availability of the small sat data. So this is commercial data. And we were fortunate to be able to use sort of 100 million square kilometers of imagery, but that gives us basically Ghana with our mapping approach. What I would love to see is, sort of more open, sort of public-private partnerships that make these small sat data publicly available, similar to the Landsat and Sentinel archive, which might be, a dream, but there's already a good start with this with the Norwegian government's agreement with Planet and Airbus to make their base map imagery available, a lot of their archived imagery available for mapping deforestation and other sort of sustainability questions in the global tropics. So that represents a good step forward in that, but if we can really get at these dynamic land cover types, if we can get more of these types of archives available for people to use. So that's all I have to say, and I'm happy to answer any questions that you might have further on that. Thanks.
Great, Lyndon, thank you so much for such a great talk with beautiful slides, I might add. So let's give it up for Lyndon and the reactions, and we can get to some questions. There's a whole bunch of them in Slido. So first, the easy one. Is your labeling platform open or available, or is that just internal in your Clark lab?
It's not yet, but it will be. So everything I'm doing is mandated, all the data, and all the data and code will be open. Some of the machine learning code for the active learning is already open. And the labeling platform code isn't open simply because I've got to clean up some locked in credentials in GitHub before I release it and get my keys hacked and that sort of thing. But yeah, that'll all be open.
All right, great. Well, we would love to share that with our community whenever it's available. So make sure to send it our way. What about this one? Have the UNet segmentation results been verified through ground truth, not over-segmented?
No, we have not gotten as far as doing that. We did collect some data on the ground early on in 2018, which we've done a bit of comparison with the random forest-based segmentations. The ones, that's what we've done most of our mapping with, but it's actually ends up not being that informative because the definition, the way that people define the fields on the ground is actually not necessarily what a field is, and it's different than what you see with an image. So I don't actually think it's necessarily the best way of verifying it. So we limit our validations to what we consider to be the best possible, human drawn boundary around a crop field. Because our experience is so far that we don't really have we haven't had good enough data on the ground to make it a meaningful apples to apples comparison, if that makes sense.
Gotcha. All right, great. Let's see, Matt, your question has been voted up. When labeling and misregistration between base layers is when labeling is misregistration between base layers a problem? Do you have to do anything to register them? If so, how do you determine an absolute location?
So that's a good question. We don't, so if you talk about the base layers in like the Bing or Google satellite based maps, we don't actually label on those. And that's not really a registration issue so much as the fact that those images are usually really outdated compared to the PlanetScope imagery that we're trying to label directly on that because we want to draw the fields that we can see in the PlanetScope imagery because we know it's sort of contemporary. That's the thing that's being classified. If we labeled on base maps, that first slide I showed about how dynamic these systems are is the type of problem you get if you try to look at a base map. And I think it's actually illegal to digitize on base maps, according to terms of use, if you dig deep into the terms of use of some of those. So, but it's not worth your time if you're trying to classify imagery in a particular year, you might have the agriculture that you're seeing in a base map is completely different than what you might get in the image you're trying to actually classify.
Gotcha. So I had a question. You mentioned in one of the kind of workflows of where you got to, you said, and then we get to analysis ready data, and then we go, then off. Could you, in your role in the machine learning community, what does that mean to you? We had a session on analysis ready data. That's a term often used. And I was just wondering what analysis ready data means in your context within machine learning.
All right, so first, a big part of the analysis ready data is already done by Planet themselves. They, convert everything to surface reflectance and orthorectify it. So that's sort of the big thing. But when I mean it within the context of our workflow is we defined a tiling unit, and then we clipped everything to every image that intersected those tiles down to the level of that tile with a bit of overlap, a little bit of extra edge and buffer for it, and then we feed that into the compositing algorithm that we developed. So the analysis ready is sort of clipping orthorectified surface reflectance data to the dimensions that we need it to create our composites.
Gotcha. So an area of interest sort of issue. Gotcha. All right. Well, we have time for one more question, and let me see. Dave has a really easy one. So where was the opening animation of deforestation?
Oh, sorry. Yeah, I should have put that on. That I actually grabbed from Earth Engine's animations. That's somewhere, I believe that is in Madagascar.
Okay, thank you. Well, let's give it up one more time. That was a great talk. And Lyndon, same thing I had with Hannah. There's a couple more questions for you in Slido. If you wanted to check those out and drop any answers in the chat, that would be great. And hopefully we have had some other really interesting conversation over in chat, and we can get back to those questions after Lexi's talk, because I think we would really love to hear what the panelists' insight. So panelists, if you want to get a jump on the conversation, one of our community members, Lewis, mentioned the notion of semantics with machine learning related to the labeling. So if you want to give some thought to that, maybe after Lexi's talk, we can jump in. My Slack is blowing up with people suggesting that we talk about that later. So I don't want to cut Lexi's time short. So Lexi, I will let you take it away. So first I'll test your audio and your screen sharing.
Is it showing up?
Yep, you bet. We can hear you and we can see your slides full screen. So take it away.
Audio is good too?
Awesome. Yes.
Okay, thanks Lyndon and Hannah's great talk. Here in the next 20 minutes, I wanted to share our experiences in the GeoAI in the domain and to share the successful stories of the GeoAI, how it has been revolutionizing the way we see the world and how we connect to each other in this new era of the GeoAI. So I'm Lexi Yang. I am a research scientist in the GeoAI group at the Oak Ridge National Laboratory. So since I joined Oak Ridge about 5 years ago, and that's when I also witnessed the whole emerging artificial intelligence, the fast-paced developments in this area, and also how this AI play an important role in the geographical data science. So I wanted to spend few minutes to give some of the information, or you already have known that GeoAI is starting providing amazing benefits and advantages in our daily lives. For example, the takeout you ordered last night from Google, Uber Eats or DoorDash, the drivers may actually use the most updated road mapping results from the latest high-resolution data to calculate the most accurate and the faster traffic routes to give you the food. And also, the scientists right now, they are able to do an annual updating on the environmental monitoring of the land use classification And just because we have the amazing advances in machine learning models, the imagery availability is impressive and compared to where we were 5 years ago. And also at the larger scale, GeoAI also play a significant role in, for example, for the humanitarian assistance programs. They use the high resolution data to map out the slum areas and evaluate the level of poverty and to see how much assistance or how much resources they would like to send out to help. And at the personal level, with your cell phone, when you are in a new city, you may find out that some apps can actually show you around the best restaurants around based on your location. So even just use your camera, take a photo of your environment, the city, what do you see? The app will give you the augmented view of what is around your place, the best place to visit, and the best restaurant, coffee shop to grab a coffee. So those advantages that you are enjoying in our daily life, actually, they are just part of our the GeoAI advances. So compared to where we were 5 years ago, of course, the data availability plays an important role. Right now, we're getting more higher temporal resolution data, higher spatial resolution data from satellite, spaceborne-based sensors. And the airborne and drone-based data, they are getting popular in many different applications. The spatial context provided is the centimeter resolution data. They are amazing and they hold a great potential to enable much more opportunities that can have the significant impacts. So we are dealing with so many pixels from so many different sensors. So we did a fun calculation just to see how much data, the magnitude of the data we are dealing with the high resolution imagery. So just with the 5-meter resolution, we can actually are seeing 100 trillion pixels are being collected every day, cover our entire planets. Just imagine how heavy lifted it is to extract the information from this massive amount of the data and to curate which data is the most available, what is the best suitable for each task, and identify the objects of interest to specific tasks. Just think about the problem itself. It is indeed a grand trillion pixel challenge, if we can call it. And artificial intelligence itself will be more prominent at the scale that we can see the world much more efficient than before. In addition to the image itself, made all the possible advances for GeoAI, there are additional 3 pillars made all the current status of the GeoAI. For example, you cannot have the EO data, just the observation data, the raw data, and without the labels to help you to train a machine learning model. And at the same time, the most advances in the machine learning algorithms or computer vision architectures we are using, they are highly complex and require quite a bit of computing powers to support training the model and also the deployments. So in the past 5 years, those 4 pillars kind of grow stronger, depend on each other, and establish what we are holding right now under this GeoAI advances. In particular, I wanted to note the labeling part, which Hannah and Landon, they individually point out the labeling data, the issue, and we didn't get the sufficient data to build a model. That part is I wanted to discuss more a little bit. So computer vision really made advances about back to 2012 when the ImageNet made available to researchers. And that's approximately the time all the advances in computer vision models, classification models, we have seen significant advances since then. So in the remote sensing community, we also recognize the need to push all the developments to enable the real artificial intelligence in our domain. So there are many contributors, institutions, entities from governments, and also involved engaging with the imaging vendors. They put the efforts together, and now you can see the number of data sets made available just for remote sensing data are increasing in the past 6 years. And those data sets cover different tasks, object detection, instance segmentation, which you're gonna use for identify exactly the same type of objects. However, each one should be classified individually. And also scene classifications, semantic segmentations. Altogether, roughly, we're looking at currently around 60 data sets. You might think 60 kind of data sets might not be enough, but considering the efforts behind those data sets, I would argue that the efforts to create a remote sensing label data set is much, much harder than natural RGB images that the computer vision community, they are creating. Because the images, overhead images, naturally, it's not easy to get. That's the first hurdle we have to go through. And then the labeling, the accurate labeling kind of related to the resolution provided by the data. And then you have to also identify what kind of problems we want to solve, what is the most urgency, what kind of data change is a change monitoring, is a multi-temporal data classification. So these efforts require continuous support from different stakeholders, organizations. Here, I put 3 major contributors that provide a sustainability, which means that they are generating data sets yearly or biannually, and focusing on different challenges or long-standing problems in earth science and also remote sensing domain. And this is much needed efforts, and we would like to see more collaborations in this domain and voice their need, create the data sets, and to push the whole geo AI to the next level. And another driver to push all the latest fast-paced developments, I would say, is the open source codes released by machine learning researchers, computer vision researchers. These trending efforts mitigates or even bridge the need when we try to leverage the machine learning techniques and how those techniques can be adapted to earth science problems. So that's the 2 important aspects when to build up the next level of geo AI I wanted to emphasize. So now we pretty much have, we have the data, we have the computing powers, and we have everything needed. We have the high resolution data. So we can go ahead to do whatever we need to generate data sets. So first, I want to share several successful stories that is done in our group. Now we are at the 3rd year of generating high resolution building maps, leveraging the supercomputer in our lab, the summits. And this is the project funded by FEMA and DHS. You will be surprised to learn that about maybe 3 years ago, we didn't have, our government didn't have the single basic infrastructure map to cover the whole building maps in the United States. And here we are close to the project's end, and we are updating. We essentially map out every building in United States. And this is the foundational data layers to support the government decisions in many aspects. And then we also leverage the OpenStreetMap, creating some of the label samples. We had to do some label shiftings just to mitigate noises comes with the OpenStreet data map, and to create a road mapping over the entire country, Iraq. Why Iraq or other countries we have tried? Because even on the OpenStreetMap, there are only fraction of area is covered by those crowdsourcing data layers in OpenStreetMap database. But by leveraging the high resolution data, Maxar, 30 to 50 centimeter data, and also all the, we again using a summit and also the auto shifting algorithms, we generate the samples automatically, and then we map out some of the entire country of Iraq. So we are pretty happy with what we can achieve, given the data quality, the road, the buildings, the objects we extract. The accuracy we are getting is close to 90. Then we start to think, what does the GeoAI mean beyond just producing data sets? And what is the next thing GeoAI can do in our daily life and making significant impact? Of course, we know that the data sets will always be playing an important role in many different aspects, but the data sets will be there, not really operational ready. So if we think the GeoAI, how it can be helping disaster response and even give the tiny actionable information, that will be how GeoAI can help in greater aspects. And I pick disaster response as one of the examples to examine how the current status of GeoAI can help, is because itself, disaster response, damage assessments, kind of engaging repetitive exercise by looking through remote sensing images with the different resolutions and looking to the damaged parts of the buildings, looking to how many debris, the piles presented in high resolution data. So this kind of task is exactly how computer vision and machine learning can help when we use the classification, object detection, these kind of techniques to help with the disaster response. And what if we can leverage not only machine learning and computer vision techniques, and we can also bring in those fast computing resources so we can provide real, nearly actionable information to FEMA and first responders, then that would be how we can really leveraging GeoAI in the deployment operational mode. So we had two exercises done in 2018 and 2020, where we help assist the FEMA to provide damage assessments over Hawaii for 2018 Goela volcano eruption. And the other event is last year, 2020, Nashville tornado. So in these two events, we map out those impact areas and also identify those impact structures. For Hawaii, we only can identify those destroyed buildings versus non-destroyed buildings, given the resolution of the data we are using. That's the level we can do for 2018 efforts. And for 2020 Nashville tornado, we used even higher resolution data that was collected by aerial CAP imagery. So the resolution itself is around 20 centimeter, which allowed us to do a more detailed damage assessment. So we can actually went in and classify damaged buildings into 4 different categories. So we send out the data set, the data layers with the classification results, and local practitioners, they received those data and they made the decisions and evaluate what kind of resources to be sent out. And is it the state level declaration, or it should be a federal level declaration? So that kind of decisions were made. And after this exercise, we engaged with the FEMA and also the first responders who had the data in hand. And we asked the question like, so we deliver the data, and the data itself is about 80 to 90 accuracy level of the quality. And how do you feel like that? And how this data is useful to your end? On your end, and how it was being used to help you make decisions. So that's when we had the whole discussions about the gap between the researchers who deliver the data and how the local practitioners would expect from the data itself. So for example, when we say, hey, this is the data layer with 80, 90 accuracies, for first responders, they are wondering what are the missing 20, 10%. Are they representing false positives, or they are representing false negatives? And those missing accuracies, are they from the imagery, or is simply you don't have enough the training data? So that kind of questions came up. And then they were asked, so why the model will make such predictions or misclassify some of the buildings, even though with the human eyes, they are completely destroyed, but machines sometimes just pick it wrong and classify the wrong categories. So those kind of questions made us think, can we advance our models so that we can explain more clearly how the machine learning model help and how the machine learning model made such decisions. And unfortunately, recent years, machine learning researchers, they tend to develop the very complex models, which sometimes involve the medians, parameters, and so many feature layers in between before you actually get the data sets. So even though, yes, we can get a very high predictive capabilities, but then the complex model itself are explaining the prediction from the models, this task even more challenging. And also in these 2 events, we received so many different post-event images, which means that we are dealing with highly heterogeneous data. At the same time, we have no corresponding label data available help us to do the accurate damage assessment predictions. Naturally, we wanted to go in. We went to collect the additional samples, and of course that part took quite a bit of time. And eventually, we didn't provide the data fast or accurate enough to help the decision makers to make the decisions. And more importantly, the privacy issue was emerging in these 2 events. We recognize that the UAV or ground data collections, that they are very helpful to help us to do damage assessments. But remember, when those images, they are with so high resolution that you can see the cracks in your buildings, that also means that the image itself will reveal the car tag numbers of your car. So currently we are reviewing policies to avoid and also to mitigate the privacy concerns for the next round of the disaster event support. So forward looking, there are a couple things we can mitigate those challenges. I would say the priority thing we should put our efforts will be continuously improving the generalization in a more powerful way. And interestingly, I learned at 3 different occasions that reading a book and also listen to the keynotes in the NIPS in 2019. So these 3 occasions all send similar messages, is that when we try to learn better, when we try to teach the machine learn better, and to achieve the broader artificial intelligence, we have to teach machine just to learn just like we are. For example, kids learn from forming a very high level abstract data concepts. That is called conceptual learning. And then we recognize that there are some local changes. We just have to embed those local changes into the global representation over different variables and mechanisms. For example, here I'm showing 4 different resolution data, and they all capture Wimbledon tennis court. So you can form a feature vectors to represent all the 4 different images. However, just like wavelet decomposition, the details can be encoded into local modules and to help the overall generalization capability. And another thing I would think that would be important to help even push further the current GeoAI would be putting the human in the loop in the machine learning pipeline. So Lyndon has mentioned active learning, how it can be used to do effective labeling. And also human in the loop can boost the model assurance, in particular for local practitioners. They would like to verify any data sets generated from machine learning models and computer vision models and make sure the data up to the quality they are looking for. So eventually, we would like to achieve fully automatic machine learning while we are not there yet. So hybrid machine learning, that's where we are right now. And I believe continuously making machine learning algorithm developments will eventually lead us to the fully automatic machine learning, maybe in the next 5 years. And also in our putting human in the loop has another benefit is to introduce the domain knowledge into this machine learning process. So it's particularly important in earth science domain, especially there are some physical principles that we are already using to model the physical phenomena, especially, for example, in the climate change models. You know some of the constraints that can be used to regularize how machine learning learn the model. And still, you will have some guidelines to explain the model just based on the constraints, the principles you put into the machine learning models. And the last one I would think would be the new challenge and also the opportunities in the next 5 years for GeoAI is to look into the data privacy issue while leveraging the labeling data that is the most important to advance GeoAI. So there are currently, there are a couple paradigms are emerging to try to address this issue. I want to bring one particular that is prominent in recent years, that is called federated learning. The framework itself takes care of the data collection and edge computing that can be done at the local personal level, and still preventing the metadata from data to send back to the learning mechanism, which can avoid and also mitigate the concern of the data privacy. So these are the 3 challenges and also opportunities I would think in the next 5 years that will push the GeoAI more even forward. So just like I wanted to conclude my presentation with what Tamara was saying at the very beginning. So this area is moving so fast. I'm sure next year when we gather again to IPS the meeting, the landscape of GeoAI might be already changing a lot. Some of the challenges may be already addressed just within the 12 months. And that is something we are looking forward, and also that will require all the collaborations and your efforts all together to make that happen. So last thing, I want to acknowledge my colleagues who made all the work, fantastic work possible here. Thank you.
Thank you, Lexi, so much. That was a great talk. And hold on, I've got to tell my office mate to zip it. Hey. Speaking of, after he read that book, Thinking Fast and Slow, System 1 and System 2 thinking was pointed out to me on a daily basis for like a month. So it was nice to see that book in your talk. We have reached the end of our session time, but we do have some questions for Lexi. I would note that we'd love to keep this conversation going in the coffee break. So if people do want to keep going on the specific topic when you head to the coffee break, please do so. But for Lexi, I did want to give you a couple of questions. So first, do you see any benefit or drawback to using a supercomputer like Summit at Oak Ridge over cloud-based ML services?
So that's a pretty common question we get when we are talking about using HPC to do our work, deploy the model on HPC versus choosing cloud computing. So I would put this though, 2 years ago, we were not allowed to use cloud computing for security reasons. And also, it kind of also related to the data we use. They are sitting in a moderate data range that can be on open domain. And typically, 2 years ago, those cloud computing environments, that's where we cannot put the data, high resolution data from Maxar on the cloud computing. But recently, we work with the cloud computing vendors. I think Amazon and Microsoft, they are improving their security on the cloud computing. I do see that we are moving to that venue. There are still some caveats. For example, in the cloud computing, the best scenario happens when you already have access to those data on cloud computing. So you don't have to involve a lot of massive data movement from local to the cloud. So Maxar, that's what we are using mostly for this high resolution data analytics. And it didn't happen. It doesn't happen yet, but I would think next 1 or 2 years, that's the environment that we are moving into. However, HPC offers some kind of benefits that is not so convenient on cloud computing, I would say. Sometimes we do a lot of the simulations and also hyperparameter tunings, and the throughput and also the connectivity to our working environments. Indeed, the Summit itself offers a certain level of the advantages. So I would say these two, we are using both technologies and both computing resources for our work at the same time. And also we are evaluating the pros and cons when we are doing a very large scale imagery analytics.
Great, thank you. So it sounds like in 2 years, who knows what things are going to look like? Models are changing, computing environments are changing. So check back in with you. Keep tuned, it sounds like.
The landscape is just changing so fast. We have
to. Another question for you is around the, when you were talking about disasters with the tornado and I think it was the Kilauea, did the first responders have data on the ground did the first responders have the data on the ground as they were deployed, or was their engagement mostly a post-mortem analysis? So did Oak Ridge supply first responders with those data as they were out there in the community, or has your engagement with first responders in the disasters community been post-disaster and talking to them?
So that effort, I would say that's the probably the first exercise collaboration with FEMA. So what we did in that event is we sent out the impact structures, the map, over, every 2 or 3 days to update them. What are the areas have been impacted by the lava, because the lava flow were changing day by day. So we are shipping all those data layers as soon as we have the most recent satellite images shipping to our lab. So I wouldn't say FEMA, they made a decision solely on our data sources, because there are other local responders, they collecting ground data, not necessarily images or the points, or they send out the crew to evaluate what is going on the ground. So, but the data there, I'm pretty sure that's the part of their decision ring to help them to make some of the decisions and also evaluate overall damages.
Okay, great. That's great to know that you had that direct pipeline in though, and that could have been part of the decision-making process. All right, we have time for one more question, and then I would invite everyone again within Kiko chat. You could see a tab or a room to the left that says coffee break. We'd invite you all to go there and find a topic to discuss, but I will give one more question to Lexi. And the one that we'll go with is, let's see, this top one has been upvoted. What is the role of discrete global grid systems like h3geo.org within the GeoAI world?
Let me check that. The one, I didn't catch that grid part.
What is the role of discrete global grid systems like H3Geo within the GeoAI world?
I'm not familiar with that term. I'm trying to look into okay, here. So I may not have the answer for you, but I certainly will do some research and to see how the GeoAI, the role of that.
All right, well, we can that's something to look up afterward, and maybe the person that asked that question can, do you have a eureka moment?
Yes, discrete global grid system. Okay, I learned something new today.
Hey, all right. It's a great day when we can have our invited speakers learn something new from our community as well. So with that, while Lexi is smiling and we're all getting ready to take a break, let's give her another great round of applause for a fantastic talk. I'd also applaud kind of our 3 panelists. It's been a real pleasure to see kind of these very applied examples that are impacting, having just real practical impacts and people making decisions based on the work that you are all doing. And as someone that's been in this community for several years, just seeing what's happened over the last 5 years in terms of real decision making around these types of data sets is phenomenal. So with that, we are going to end the session and invite everyone to coffee or whatever time it is in your time zone. And thank you very much.